What will actually happen when Andromeda collides with the Milky Way? Okay, I need to share something with you, and I really need you to stick with me here, because the scenario I'm about to guide you through this evening fundamentally overturns everything we thought we knew about the ultimate destiny of our home galaxy. For over a decade, we were told it was a foregone conclusion, an absolute certainty. The scientific agreement, backed publicly by NASA itself, declared that our Milky Way was locked onto an unstoppable crash course with the Andromeda Galaxy. 4 billion years from now, 2 trillion stars were destined to smash into one another in the most violent event our region of the universe would ever experience. Except, that's simply not what the current science indicates anymore. Back in June of this year, a group of researchers led by Tilsawala at the University of Helsinki published findings in Nature Astronomy that have essentially torn up that old story and started over from scratch. And what they uncovered isn't just mildly interesting, it represents a complete 180-degree turn from everything astronomers have been confidently telling us since 2012. Here's the core concept you need to grasp: the galactic collision that everyone assumed was written in stone. It's now nothing more than a coin toss, a straight 50-50 proposition. And if it does actually take place, it certainly won't happen the way we were originally told. Stay with me here, because the specific details are crucial. Let's transport ourselves back to 1912. That was the year astronomer Vesto Slipher first detected something strange about the light arriving from what we now identify as the Andromeda Galaxy. That light exhibited a blue shift. It was compressed, shifted toward the shorter wavelengths of the spectrum. Just as the siren of an ambulance climbs in pitch as it races toward you, that blue shift served as unmistakable proof that Andromeda was traveling toward us, barreling in our direction at a staggering speed. At that moment in history, astronomers didn't even realize Andromeda was a distinct separate galaxy. They categorized it as a nebula, basically just a cloud of gas floating within the boundaries of our own Milky Way. It wasn't until Edwin Hubble accurately measured its vast distance in the 1920s that humanity understood we were observing an entirely different island universe, a collection of stars situated 2.5 million light-years away. But here's the critical point. For an entire century following Slipher's initial discovery, astronomers were unable to determine whether we were facing a direct head-on impact, a sideswipe, or a near-total miss. Calculating the sideways drift of something located 2.5 million light-years away, measuring its motion across the celestial sphere, is an almost unimaginably difficult task. One researcher cleverly compared the challenge to attempting to measure the growth rate of a single human hair viewed from the distance of the moon. You really need to visualize the scale of this problem. Andromeda is hurtling toward us at roughly 250,000 miles per hour. That sounds incredibly fast, and it absolutely is. However, at that immense range, even while moving at such an astonishing speed, the galaxy appears almost frozen in place within our night sky. Detecting its lateral movement involves tracking alterations smaller than 1/1,000,000th of a degree, compiled over years of painstaking observations. Then, in 2012, everything appeared to shift dramatically. A research team utilizing the Hubble Space Telescope dedicated 7 years to monitoring the positions of stars inside Andromeda, using even more distant background galaxies as fixed reference points. By averaging thousands upon thousands of measurements, they pulled off something truly remarkable, achieving sub-pixel accuracy regarding Andromeda's sideways velocity, and their conclusion seemed definitive. Andromeda wasn't just heading our way in a general sense, it was aimed almost directly at us. A head-on smash occurring within 4 to 5 billion years wasn't merely a possibility. According to that 2012 study, it was an inevitability, as unavoidable as, to borrow Benjamin Franklin's phrase, death and taxes. NASA announced these findings with complete confidence. Headlines around the world declared the Milky Way's destruction was sealed. Computer simulations illustrated our beautiful, pinwheel-shaped spiral being ripped apart, stars flung out like cosmic confetti, both galaxies eventually collapsing into a featureless, spherical blob classified as an elliptical galaxy. Astronomers even preemptively named the resulting wreckage Milkomeda. For 13 solid years, that remained the accepted narrative. It's what everyone believed. It's the version that found its way into textbooks, documentary films, and countless science education programs. If you're finding this content valuable, I strongly encourage you to subscribe to this channel right now and activate the notification bell because I regularly cover developments in science and space exploration that will profoundly reshape your perspective on humanity's position within the cosmos. Now, this is where the story takes a genuinely fascinating turn. The researchers behind the 2012 study weren't wrong about what they actually measured. Their data was robust, their methodology was legitimate, but they were operating with an incomplete set of information. And this is precisely where Sawala's 2025 investigation changes the entire game. Just think about what that statement actually implies. You see, those original calculations essentially treated the Milky Way and Andromeda as if they existed in a perfect vacuum. Two colossal masses moving toward one another across empty space, their ultimate fates determined purely by their mutual gravitational pull. However, our specific corner of the universe, what astronomers label the local group, is far from empty. It contains at least 100 identified galaxies, with more still being discovered. And it turns out that two of those galaxies completely alter the equation. The first is the Triangulum Galaxy, also designated M33. It ranks as the third largest member of the local group, hosting roughly 40 billion stars. When Sawala's team incorporated its gravitational effects into their simulations, the probability of a merger actually increased. Triangulum's mass exerts a subtle pull, drawing the Milky Way and Andromeda marginally closer together, like a cosmic matchmaker gently nudging two dancers toward each other. But here's the unexpected twist. The second galaxy they included produced precisely the opposite result. And this particular galaxy is visible to the naked eye from the southern hemisphere. Its name is the Large Magellanic Cloud. Stay focused here, because this distinction carries enormous weight. The Large Magellanic Cloud functions as a satellite galaxy orbiting the Milky Way. It possesses only about 15% of our galaxy's mass. Cosmically speaking, that's not particularly impressive, really just a dwarf galaxy. However, its orbital path runs perpendicular to the direction we're traveling relative to Andromeda, and that perpendicular tug-of-war is significant enough to pull the Milky Way slightly off its original trajectory. Allow me to restate that so it fully registers. A galaxy weighing just 15% of our own mass, orbiting at a right angle to our course, holds the potential to divert us from a collision involving 2 trillion stars. It's analogous to walking down a sidewalk directly towards someone, and at the very last moment before impact, a friend grabs your arm and yanks you just slightly sideways. You might still brush shoulders, you might miss entirely, but that small sideways force introduces just enough deviation to inject genuine uncertainty into the outcome. Sawala's team executed 100,000 distinct simulations, employing the most up-to-date data from both the Hubble Space Telescope and the European Space Agency's Gaia mission. They accounted for 22 different variables. They incorporated every measurable uncertainty regarding the positions, motions, and masses of all 4 major galaxies involved. And here are the results they obtained. The probability of an actual collision occurring within the next 5 billion years? Not certain. Not even likely. Just 2%. The probability of any collision taking place within 10 billion years? Roughly 50-50. A literal coin flip. Furthermore, if a merger does eventually occur, it won't happen within the originally predicted 4 to 5 billion year time frame. The most probable timeline places it around 7 to 8 billion years from now, nearly double the interval calculated in the 2012 study. Think carefully about what that signifies. For 13 years, we were told the destruction of our galaxy as we recognize it was 4 billion years away and absolutely guaranteed. Now, we're discovering it might never happen at all. And if it does occur, it's almost twice as distant in the future as we previously believed. Roland van der Marel, one of the principal astronomers behind the original 2012 research, openly acknowledged the irony. Despite possessing even more precise Hubble data now than they had back then, we are actually less certain about the final outcome. This is because the more complete analysis revealed just how dramatically the other nearby galaxies affect the situation. Drop a comment right now and tell me exactly where you're watching from. I genuinely want to understand how far this information is traveling across the globe. Now allow me to connect a few additional points because you might be raising a particular question. Does any of this actually matter to us, to Earth, to humanity as a whole? Here's the honest response. No. And that's not a dismissive answer. It's actually part of what renders this story so profoundly intriguing. You see, long before Andromeda could ever physically reach our location, Earth will have already become completely uninhabitable, not due to any galactic collision, but because of our own sun. The sun is 4.5 billion years old. It's middle-aged as stars go, and over the next billion years, it will gradually increase its luminosity by approximately 35 to 40%. That may not sound catastrophic, but it's more than sufficient to trigger a runaway greenhouse effect on our planet. Our oceans will boil away completely. All terrestrial life will meet its end roughly 1 billion years from now. Earth will transform into a scorched, barren rock. And that occurs a full 3 billion years before the earliest possible collision scenario. In about 5 billion years, the sun itself will exhaust its supply of hydrogen fuel and expand into a red giant star, very likely engulfing Mercury, Venus, and possibly Earth itself. So even if humanity somehow survived the runaway greenhouse effect, the sun's eventual death would complete the destruction long before any galactic merger could threaten us directly. Therefore, humanity, or whatever we might evolve into, simply won't be present to witness the fireworks, not unless we figure out how to relocate our species to an entirely different star system. However, this next part is where the concept becomes genuinely mind-bending. If you could somehow observe the collision from a safe, detached vantage point, here's what the simulations predict would actually unfold. First, despite what your intuition might scream at you, almost no individual stars would actually collide with one another. Let that sink in for a moment. Two immense galaxies containing a combined total exceeding 1 trillion stars would pass directly through each other, and the statistical likelihood of any two specific stars physically impacting one another is essentially zero. Here's the reason why. Space is incomprehensibly, almost offensively, empty. If you compressed our sun down to the size of a ping-pong ball, the nearest star, Proxima Centauri, would be another ping-pong ball positioned roughly 700 miles away. The average spacing between stars in our galaxy is comparable to placing one ping-pong ball every 2 miles. Consequently, when galaxies collide, they don't smash apart like cars in a demolition derby. They pass through one another like two immense clouds of gnats. The individual gnats almost never make contact, but the clouds themselves become wildly distorted by the gravitational forces involved. And that gravitational distortion is where the real drama originates. Picture what the night sky would resemble as this process gradually unfolds. Approximately 3.5 billion years before the initial contact, Andromeda would begin to appear noticeably larger in our field of view. Right now, it presents as a faint, fuzzy smudge, roughly 6 times the diameter of the full moon. But as it drew nearer, it would continue growing and expanding until it completely dominated the night sky, a vast, luminous spiral stretching from horizon to horizon. At 375 billion years from now, the preliminary collision phase begins. The sky would brighten dramatically as compressed gas clouds ignite a furious burst of new star formation, thousands of new suns igniting simultaneously, illuminating the darkness. By the 4 billion year mark, both galaxies would exhibit visible warping. The elegant spiral arms of the Milky Way would become stretched and contorted. Andromeda would appear tidally elongated, pulled apart by immense gravitational stresses. The thin, disc-like structures characteristic of both spiral galaxies would stretch and warp beyond recognition. Tidal forces would hurl long streams of stars spinning off into intergalactic space. Our own solar system, currently positioned about 26,000 light-years from the galactic center, could be completely relocated, tossed out to the far suburbs of the merged galaxy, or perhaps ejected entirely. The simulations indicate a 12% probability that our entire solar system gets thrown completely out of the newly formed galaxy during the merger, simply expelled into the void between galaxies. And here's the remarkable part. That outcome wouldn't necessarily spell disaster. The sun would continue burning steadily. The planets would maintain their orbits. We would simply find ourselves drifting through intergalactic space, watching the cosmic chaos recede into an ever-increasing distance. By approximately 5 billion years after the encounter's initiation, the cores of both original galaxies would appear as two brilliant lobes in the sky, circling one another in a gravitational dance, requiring another 2 billion years to complete. And by 7 billion years, the merger would be finalized. Both galaxies, now fully combined into a single, enormous elliptical galaxy. No more spiral arms, no more elegant disk structure. Just a colossal, spherical aggregation of stars slowly aging together in cosmic solitude. If you're absorbing information you didn't previously possess, please hit that like button right now, because this story is about to become even more extraordinary. Let me now discuss the black holes. At the very center of the Milky Way resides Sagittarius A. It's a supermassive black hole, roughly 4 million times the mass of our Sun. Sounds enormous, correct? It absolutely is. However, Andromeda's central black hole makes ours appear almost modest by comparison. The black hole at Andromeda's core possesses a mass somewhere between 100 million and 200 million solar masses, approximately 50 times more massive than our own, a true cosmic heavyweight. If the galaxies do merge, these two gravitational monsters will eventually begin spiraling toward one another. It would take millions of years following the initial galactic collision for them to draw significantly close. The process unfolds gradually, driven by a phenomenon known as dynamical friction, as each black hole interacts gravitationally with the surrounding stars and dark matter. But once they approach within approximately 1 light-year of each other, they will begin radiating gravitational waves of such immense power that the energy loss will rapidly drain their orbital momentum. Then they will merge, creating a single, even more massive black hole anchoring the center of the newly formed elliptical galaxy. The gravitational wave signal emitted by such an event would be staggering. Current detectors like LIGO cannot capture mergers of supermassive black holes, but future space-based observatories such as the European Space Agency's LISA mission should be capable of detecting similar events occurring in distant galaxies. We may one day observe, indirectly, what the ultimate fate of our own galaxy's central black hole would resemble. The gas funneled toward this combined black hole during the merger could generate what astronomers term an active galactic nucleus. Essentially, the black hole would begin actively feeding, and the material spiraling into it would emit tremendous quantities of radiation before crossing the event horizon. From a safe distance, it would constitute one of the most energetically spectacular events imaginable, the birth of a cosmic monster at the heart of Milkomeda. But I want to redirect focus back to what the 2025 research actually communicates to us, because here's what the majority of people are missing. The headline isn't really about whether the collision occurs or not. The deeper revelation concerns how much we still do not know about our own galaxy, about the forces actively shaping its destiny, about the cosmic neighborhood we call home. Sawala articulated it this way, quote, "Even using the latest and most precise observational data available, the future of the local group is uncertain." Ponder that statement. We possess the Hubble Space Telescope. We possess the Gaia mission, which has mapped the positions and motions of nearly 2 billion stars with unprecedented precision. We possess supercomputers executing 100,000 individual simulations, and we still cannot state with confidence whether the two largest galaxies in our immediate vicinity will eventually collide or not. That is not a failure of science. That is the humbling reality imposed by cosmic scales. Measuring the sideways motion of a galaxy 2.5 million light-years away remains comparable to measuring hair growth from the moon. Even equipped with our finest instruments, uncertainties compound relentlessly. A tiny error in mass estimation here, a small uncertainty in velocity there, and across billions of years, those minute discrepancies cascade into entirely divergent outcomes. Geraint Lewis, a professor of astrophysics at the University of Sydney who has extensively studied this question, offered a sobering perspective. Even if the galaxies avoid a direct head-on impact, a close encounter would still prove devastating. The gravitational tearing each galaxy would inflict upon the other would very likely leave both in what he termed a sorry state. Therefore, even the optimistic scenario isn't exactly peaceful. Two massive galaxies passing within a few 100,000 light-years of one another would still significantly disrupt both structures. Stars would be scattered, orbits would be altered. The familiar configuration of the night sky would be permanently transformed. Professor Carlos Frank from Durham University, one of the study's co-authors, said something that has lingered with me. Quote, "It is amazing that we are able to simulate the evolution of gigantic collections of stars over billions of years and figure out their ultimate fate. This is a testimony to the power of physics, allied to the power of large supercomputers. But even that remarkable power has inherent limits, and the universe, it seems, still delights in keeping us guessing. Now, here are the developments to monitor moving forward. The Gaia Space Telescope is scheduled to release new data in the summer of 2026. That forthcoming data set will include more precise measurements of one of the most crucial variables in this entire question, the transverse motion of Andromeda. Essentially, how fast it's drifting sideways across the sky, not merely rushing toward us. Those refined measurements could significantly shift the probabilities. We might learn that the collision is more likely than the current 50-50 estimate suggests. Alternatively, we might discover that our galaxy is genuinely safe from such a merger for the next 10 billion years. Either way, the story remains far from finished. The science continues to be written in real time. There is also ongoing research into the dark matter halos enveloping both galaxies. These invisible structures contain the vast majority of each galaxy's mass, and their precise extent and density profoundly influence how a collision would unfold. Improved mapping of dark matter distribution could further refine our predictive models. Allow me to leave you with three final thoughts. First, the Andromeda collision, which we were repeatedly told was an absolute certainty, is now anything but, a coin flip at best, and possibly not happening at all within cosmically meaningful timescales. The inclusion of the Large Magellanic Cloud in the calculations fundamentally changed the equation. Second, even if it does eventually happen, individual stars will not collide with one another. The event would be gravitationally violent, but not physically destructive at the stellar scale. Our solar system might be relocated or even ejected, but the sun and its planets would very likely survive intact. The night sky would transform into something utterly unrecognizable, yet the stars themselves would endure. Third, and this is the idea that truly stays with me, we are living in an era where we can simulate the fate of 1 trillion stars across billions of years. We can peer 2.5 million light-years into space and track the motion of individual stars against the cosmic background. And yet, the universe still retains its secrets. The outcome of the single largest event that could ever affect our galaxy remains genuinely uncertain. There exists something profoundly beautiful within that uncertainty, a reminder that even with all our instruments, equations, and supercomputers, the cosmos operates on scales that dwarf our comprehension. The Milky Way might survive another 10 billion years as a recognizable spiral galaxy, continuing to form new stars and new planets and perhaps new civilizations that will gaze up at their night sky, wondering about their place in the universe. Or it might eventually merge with Andromeda, its graceful spiral arms torn away, its stars scattered into an enormous elliptical aggregation where new star formation gradually grinds to a halt and the night sky becomes something entirely different. We do not know which future awaits us, and right now, the science indicates we cannot know, but we can watch, we can measure, we can continue asking questions. And that, ultimately, is precisely what makes us human. Make absolutely sure you're subscribed with notifications activated, because when that Gaia data arrives in 2026, I will be right here to explain what it means for the future of our galaxy. I'll be watching, and so should you.